Today is April 16th, 2020. My name is Ted Doskaris, and I'm going to describe and demonstrate that the USA Trains GP38 here, and this is basically a factory unit, and the USA Trains SD40-2, which is also a factory unit, that the GP38 will actually run faster on a test track, or on any kind of track really, than the SD40-2. And just to describe what things that I have done to these is that I've replaced the traction tire wheels in the trucks, front, rear, and front, and both of these units, front and rear, with regular solid metal wheels that are just like the ones in the opposite end here, or in the case of the SD40-2, the middle axle. So this is the axle that I took out, for example, of front and rear, and this is the axle that I took out again from the front truck and the rear truck. It's the axle closest to the fuel tank in both cases that USA Trains equips with traction tires. Now they were replaced with solid metal wheels because, as George Schreier described in his website, he's a scientist engineer, and he discovered when using pulse width modulation or a form of pulses on the track, as opposed to just a plain DC value, that the wheels can become pitted. And it's because of the characteristics of the motors that USA Trains employs in these units. And he describes it as current inrush when pulses are applied. So apparently he discovered the wheels can pit. Now I use track power, and many people use track power. So one advantage of replacing these wheels is to give more contact patch area in addition to the skates and the other axles. In this case, in the case of the SD40-2, the floppy axle here is electrically dead. It doesn't contribute any electrical pickup. It doesn't have any axle tips that go into the side frames, for example, like the other axles. So in the case of the SD40-2, electrical pickup is afforded by the wheels and the skates, and of course, similarly with the GP38, it's the same. Now the F3 and the GP9s and the GP30s all use this same motor block and same truck here. So another thing to point out is the difference in wheel sizes. The wheels on the SD40-2 versus the GP38 and its siblings, like the F3, GP30, and so on, the wheel diameter is fairly small on these things, and it's unrealistic actually. And the wheel diameter on the SD40 is more realistic, but it's even under scale if you try to scale it up. Both of these are locos, or 129 scale models, and it's about 10% smaller than what it should be, but it's reasonably close. Whereas the two-axle trucks that are used in the motor blocks with the wheels that are used in the GP38 and GP9s and so on, they're really so small. They're actually more suitable for scale-wise if it were a 44-tonner GE locomotive. So at any rate, another thing to point out is the difference in the gears. Even though this unit has small diameter wheels compared to this, you would think it would run slower. But because of the gearing within the unit, you can see there's a difference in gear sizes here. This is the SD40-2, and this is the GP38. The difference in there's enough difference in gearing, how they've chosen to gear this thing, that this unit, in spite of the small wheels, it'll actually run faster than the SD40-2, and that's what I'm going to demonstrate in a little bit. So at any rate, another thing I'm going to describe is, because of the current inrush characteristics, George Schreier established through experiment and theory that if you put low value resistors in series with the motors. In series with the motors, not the power pickups from the wheels in this case, but in series with the motors in both of these things here, both these units, that you can minimize the effect of wheel pitting. And so in the case of the GP38, I have a switch here down here, and it's in a position where it says off. I've marked it with labels here. If I throw it this way, it engages the resistors. So I did one of these locos like this just to see the difference in the speed running characteristics. So normally I would favor using the resistors, but right now I've got it in the off position, so that means that it's like the factory had set it up, as the resistors are not engaged. Now in the case of this particular SD40-2, it's my Southern Pacific one, I did not yet put resistors in it. It does not have the current inrush resistors in it. So I'm going to run these locos on a test track here, and we'll see how they operate. But before I do, I want to describe, here's my test track here. It's a circular 8-foot diameter track. And I'm going to describe, first of all, using an oscilloscope so we can actually see what the voltage looks like when it's applied to the rails. So the oscilloscope here I'm using for this test, it's set up for two channels, channel A minus B, and channel B is inverted, which means B is subtracted from A. So it's differential. So it's set up for 5 volts per division. These are 1 centimeter divisions. This middle trace here is the center part of the screen from left to right, is the reference. So that'll be 0 volts, since I haven't applied a voltage yet. And sometimes it's called ground, but that's the reference. So I'm using an Aristocraft, an older train engineer here, and you can see the power supply and the receiver here. Right now it's set up for slide switches in linear, and I'm going to, and what I've done was I have 2 GP38s that are identical, except for the front one has the switch that I previously described, and the switch is thrown right now without having current inrush resistors in series with the motors. The back, the unit on the back has the resistors installed. I didn't put a switch in it because I didn't feel the need to do that any longer, since I was satisfied with the results from the one with the switch, because the switch requires more wiring and it didn't seem necessary to do that. So I'm going to run it now, and what will be observed is the factory unit that's on the front in the factory mode with the switch thrown so the resistors are not in series with the motors will run just a little bit faster than the one with the resistors in it, which is the rear one here. So I'm going to increase the voltage. You can see here. So it's linear, so you don't see any pulses. And we can see, and I'll speed it up here a little bit more, there's not much difference in speeds, but the one without the resistors in series with the motor is going a little bit faster. You can see it's separating ever so slightly, especially if I increase the speed here. So now I'm going to reverse it, and we'll see that on the oscilloscope here. And you can see the voltage is going negative now. Now we will expect the unit on the right hand side to catch up with the one on the left hand side, because again the switch is thrown so the resistors are not in series with the motors. So they're caught up to it. So that describes the difference and shows the little difference between speeds when using a 1 ohm value resistor, which is what I'm using here. So at any rate, I will now demonstrate with pulse width control, or pulse width modulation. Aristocraft calls it pulse width control. So I'm going to switch now the receiver to PWC. Turn back on the power supply there for it. And first of all, I'll have to synchronize the waveform here. So the pulse doesn't look too elegant here. But we can see that the pulse goes from, should use a different pointer, from our reference 0 point here to about 16 volts. Since it's 5 volts per unit here, it's about 16 volts. And the locos here aren't moving, but you can see the lights are on. That's one advantage of PWM, or PWC as Aristocraft had called it. So as we increase, and it's running at 41.67 microseconds between occurrences of the pulse, and you can see there's several pulses here. So there we go. So that's about 24 kilohertz, or 24,000 times a second. So at the rate of the pulses. So as I increase the pulse width, actually the voltage, ideally it would be a square type wave where the edges would be squared off, but things aren't perfect. So we can see here how the locals will operate. So again, the one with the switch thrown so that it's in the factory-like mode where there aren't any resistors in series with the electric motors in the trucks. That is a little faster. So now I'll reverse it. And I have to resynchronize the scope here. Put it in negative slope. There. So now we can see the zero reference is going minus, so about minus 15 or so volts, or 16, 17 volts. So we'll see what happens. And you can see now the loco without the resistors engaged, it's catching up to the loco that has the resistors, which is on my left. So they're caught up. So it's not a big difference, but this goes to show you there is no difference whether you're using linear or whether you're using pulse width modulation as to the effects of having the resistors, insofar as speed differences, of having the resistors in the unit versus throwing the switch for having the resistors out of the unit, as in the case of the lead unit here. Now I have thrown the switch in the lead unit here, so the resistors are engaged. So now it'll be like this unit here where the resistors are just hardwired in there without any switch. So we'll just see how they operate then. So one wouldn't expect that there'd be much difference at all then. So there's very, very little difference at this point here. So now I'll reverse it. So any difference is really the tolerances involved with the motors, the gearing and so on, how the lubrication is, and any tolerances of coming from the factory. So I'll separate them a little more so it's more visible. So again, with both locos having the resistors engaged, there's little difference. But the more important point is, whether the resistors are engaged or not, there's not much difference in speed between these. And also, whether it's operating on linear or whether it's operating on pulse width modulation, or PWC as Aristocrat called it, it doesn't make any difference either. Now I put the Southern Pacific SD40-2 on the test track that does not have current inrush resistors installed at all. And now, that's for the motors. And now also I put the GP38 on the track that the switch is thrown so the resistors are not effectively installed. It's just like the factory wiring. So I'm going to run it starting on linear here, and so here's linear. So you can see that there's not any pulses there. So we'll see what happens. So we can see gradually the GP38 is closing in on the SD40-2. So again, in both cases, the resistors are not, there aren't any resistors in series with electric motors in either the Southern Pacific unit, which I never installed them in there yet, and the switch on the Rock Island locomotive, the GP38 behind it, is thrown so the resistors are not engaged. It's just like the factory wiring now. So now I'll reverse it, and so we can see on the oscilloscope here the value is going negative. It's a level level trace here, DC. So ever so slightly, the GP38 is gaining more distance from the SD40-2. So much for chasing it around the track. So now I'll put the power supply in pulse width modulation. So I usually, for safety's sake, turn off the supply to the receiver, put it in TWC, turn on the supply, and got to synchronize the scope here. Put it in positive. Triggering right on the scope here. There. So it's about 50% modulated. So it's not a big difference in speed still, but you can see the GP38 is catching up to the SD40-2. So it is the faster of the two locos, all else being equal. Now we can see here with pulse width modulation, the more I run it up, the faster speed becomes a level. And so if I slow it down, oops, I hit reverse by mistake. So we'll re-trigger it. I can resync it. There. So they're going in the reverse direction now. So I'll slow it down. So the pulse is negative now from the center trace here is our reference 0, and it's going negative. So you can see as the pulse width is decreasing, it's a crappy looking pulse, but that's the way it's designed. That the GP38 gained quite a bit of distance, as you can see here, while I wasn't looking at it. So again, the distance is starting to close up a little bit with the GP38 running faster. It's not a big difference, but it is different. So definitely the GP38, without any current inrush resistors in series with electric motors, and with the SD40 not having those resistors either, the GP38 is faster. So being the motor blocks in the GP38 are also common with the GP30, the F3, and the GP7/9 of USA Trains. There wouldn't be any difference between them if you were to use a one of those units along with an SD40-2. So there you have it. Now I put the receiver back into linear mode, not that it's going to matter really, as I've demonstrated before. But and I threw the switch on the GP38 here, so the 1 ohm current limiting inrush resistors are, there's one resistor in series with each electric motor. So then that'll slow down the GP38 a little bit as a byproduct, so to speak. And I think what I'll do for this demonstration is bring the locos closer, because the speed won't be that much difference. So in this case, the GP38 was slowed down just a little bit, but it's almost the same speed now of the SD40-2. So again, the SD40-2 does not have current limiting inrush resistors, and now the GP38, the switch is thrown so the 1 ohm current limiting inrush resistors are, for the motors, are connected. So it would appear though that the GP38 now is running a little bit slower, but almost the same speed of the SD40-2, and that would be expected. So there you have it. And again, these locos I'm using, they're essentially brand new locos as received from the factory, just with the alterations that I described earlier. So I'll run it in reverse now. Getting dizzy running around in a circle here. So the SD40-2 is yet to catch up with the GP38, even with the resistors in series with the electric motors. So there's not much difference between them. But whether or not the resistors are installed in, say, the GP38, with no resistors installed with the SD40-2, the speeds are pretty close, and they operate all right together either way. There you have it.